I hope my screen is visible.
Yes, visible.
Okay. Yeah, so welcome to the second session on design and analysis of algorithms course. So in the first week, we had covered, the basic notations, or rather the standard notations that we use to analyze an algorithm or a function. So essentially, it's like you have a function, and the input is some parameter n, which is some integer. So you have a function. You want to understand the growth of that function with respect to the input parameter n, right? Or you want to compare two or different functions, right? Which one grows faster, and so on. So for that, we had discussed the big O notation, omega, and the theta notations, and we did some examples as well, right? So this you might want to uh, remember, and it's quite useful whenever we have functions involving factorials, right? So sometimes it helps using the Stirling's approximation to get the growth of the function. Okay, so in week 2, the plan is now to look at algorithms. We will also do the analysis, but then, as I had mentioned in the previous session, that the analysis won't take much time, right? So it's the design of algorithms where we have to spend more time. Okay, so as per the course schedule, I think this week or the week 1 was about searching and sorting algorithms. I hope you understand the sorting algorithms, right? All the sorting algorithms, the basic ones like insertion, selection, merge sort, quick sort. Uh, is heap sort also covered in that course? Anyway, so maybe heaps, because that will be discussed in the later in the later weeks. Maybe heap sort will be covered then. So we will see like one divide and conquer based sorting algorithm, either merge sort or the quick sort. And before that, I would like to spend some time on the other two simple algorithms, like the selection and the insertion sort, right? So, and even before sorting, let me quickly discuss the searching, right?
Hello.
Yeah. Any question? Yeah, we will discuss this thing in the last 5 minutes or so, because I haven't enrolled in the course, so I don't know what editor you are using for programming assignments, right? So, and that should not be much of an issue. I've done these courses in the past and I hadn't faced such issues. So searching means you are given a list of elements and you want to search for an element in that list. Right? Well, let's say we have the elements which are comparable. And when we say that the elements are comparable, it means that you can sort them. Right? So let's say the elements are, for instance, if you have integers or strings, you can compare them. Strings you can compare on the basis of dictionary ordering, right? So if I have two strings, one is starting with the alphabet A, another one is starting with B, then I know that the one is starting with A comes lexicographically, it comes before the one that starts with B, right? So all such data which are comparable can be sorted. Now, let's say I have a list of elements and I want to search for an element. So if it is not sorted, then the only option to search is you have to go through the entire list, right? So what would be the running time in that case? So please keep yourself muted. If you want to ask question, then you can unmute yourself. Yeah. So yeah, so if we want to search for an element in an unsorted list, how much time it is going to take in the worst case?
It's a O of one, O of n, sorry, O of n.
O of order n, right?
Yes,
So in
yes.
unordered list, so you have to scan the entire list and therefore the running time would be worst case order n, right? Then if my list is sorted or ordered, then can we do better?
Yes, it is log n.
And why is it so? Login?
Because every time the half of the partition of the list is going to be ignored. So we go
Yes.
for left off or right off based on the key element you are searching, right?
Exactly, right? So if I have a list of n elements, right? So I have n numbers, let's say x1, x2 up to xn, then I go and first of all check the middle element of the list, whether it is the one I am looking for. If it is not, then since the list is ordered, I can compare the element that I am searching for with the middle element. And then based on the ordering between these two lists, these two numbers, right? These two elements, x and the middle element, let's say xm, whichever is a smaller, let's say x is smaller than xm, then I will search in the first half of the list. Or if x is larger than xm, the middle element, in that case I am going to search in the second half, in the right half of the list. So what happens is in every iteration my search space reduces by half, a factor of half. Okay, so initially the search space was had size equal to n, right? Then after first iteration it becomes equal to n by 2. Second iteration n by 4, right? So it's the reduction in the search space. The search space keeps reducing by a factor of half. Okay, so initially it is n, then it goes down to n by 2. So since we are discarding half of the space in every iteration, then you can see that it will only take me log n many iteration to eventually either we'll be able to find the element or we will just, and it's essentially we have not scanned the entire list, but we'll be able to say whether the element is there in the list or not. Okay, so if it is ordered, then the running time would be big O of log n. Okay. And this search is known by, when you have sorted list, the kind of search that we discussed, wherein we go and compare with the middle element, and then based on the middle element and the element that I'm looking for, based on the comparison between those two, whether we want to discard the left half or the right half. This kind of search is known as the binary search. So in case of ordered list, we are going to use binary search. And in case of unordered list, where you have to scan the entire list, that is referred to as linear search. Now, if the list is sorted, it really helps, right? So one question is, how do we sort the elements in the list? So again, for that, the elements must be comparable. And let's say I have a list of comparable elements. I want to sort the list. There are multiple techniques, multiple ways of sorting a list with different running times. There are divide and conquer based algorithms like merge sort and quick sort. So we'll see one of the two in the second half of the session. And then there are other algorithms, right, which have the worst case running time of quadratic running time, order n square, like maybe bubble sort, selection sort, insertion sort. So let me spend just a few minutes on selection and insertion sort. Can someone explain the selection sort? See, I'm spending some time on these basic algorithms because we will see a nice problem, geometry problem, and there we would like to, use some of the ideas from selection sort or something based on sorting, to solve those problems. So how do we, how does selection sort help? What do we like? Is this an iterative algorithm? What kind of algorithm is this? And what do we do in each iteration in the selection sort?
Yeah, it is iterative one only.
Mm-hmm.
Every time we select, the minimum element index position,
Yes.
and that in minimum index position, yeah, it could be if it is first minimum, we'll place in
Mm-hmm.
the first index position, and then we
Exactly.
select the second minimum, something like that. Yeah, it goes to that every element,
Exactly.
right? Yeah.
Yes. So we have a list of n elements, and because it's an unordered list to begin with, we have to do a linear search in the entire array to find the minimum element. Right? So it's like searching for the minimum element. So selection sort is in every iteration, you search for the minimum element in the list that remains. So initially I have the full list. I want to find the smallest element. So you do a linear scan, which takes order n time. And let's say the minimum element happens to be at index I, then you're going to replace the element at index I with the element at index 1 so that the smallest element is now at the first index, right? And you repeat this process. After this process, your list size reduces by 1 in the sense that the elements that you want to sort, that reduces by 1. So you have the remaining n minus 1 elements. Again, you go on and find the smallest element in those n minus 1 elements, and you swap it with the element at index 2, and so on and so forth. So in every iteration, first iteration takes order n time, then order n minus 1, sorry, n time n minus 1, and so on up to 1, which sums up to order 1 plus 2 plus up to n is, what is the running time?
It is n into n plus 1 by 2, something like that. Yeah, because
Yes, it is n into n plus 1 by 2, which is big O of n is squared,
correct, n
right?
square. Mm.
So this selection sort involves searching for the minimum element in the list in each iteration. right? And therefore the running time is order n squared, n plus n minus 1, and so on up to 1, which is big O of n squared. Okay, and then what do we do in insertion sort? How does insertion sort works? Yes. See, at least you should watch all the videos in the course, whatever, for that week. So these basic things should be clear, right? Otherwise, how would I know whether you know these or not? And if I start covering more advanced things, then it won't help you much. So how many, like, have you not seen insertion sort before?
Then I think in this case, in selection sort, we have to first uh, first we take the zeroth element at the minimum, and then the next element
Huh?
we compare it with the first one. If it
Yes.
is lower, if
Huh?
it is lower than that, then we put it in the first position,
Yes.
and then we move to the third element.
Huh?
Then we find out what should be its position with
Yes.
respect to the previous two,
First two
and with
elements.
the first two elements, and in this way we continue.
Continue. Exactly. Right. So the idea is, so let me draw the figure, or not the figure, but just as an example. Let's say I have uh, I have like first k elements which are sorted, already sorted, right, via this selection sort. Oh, sorry, insertion sort. So x1, x2 up to xk. Let's say this part is already sorted. And now I have this next element xk plus 1. And what we want is uh, in this particular iteration, what we want is this entire list must be sorted. Okay, so the first k elements are already sorted via the approach that I'm going to explain to you. And after this iteration, I want that this entire list must be sorted. The list of size k plus 1. So in every iteration, we want to extend the size of the sorted, the part of the input array that we have sorted by 1. We are going to increase its size by 1. So the simplest way to do is you want to insert this element at the correct position in the sorted list. So what we are going to do is, we are going to compare this with the previous element. So I'll compare this with xk. And if if xk plus 1 is larger, then we don't do anything. We just stop and we report that, this is the sorted list. Otherwise, if xk is smaller, I'm going to shift it to the right, Shift it by one position to the right. And then we know that xk plus 1 can come here. So we are not going to swap the things, just shift xk by right, by one position to the right, and then continue that, right? Next, we are going to compare xk plus 1 with xk minus 1. Again, if xk minus 1 is larger, we are going to shift it to the right. So when do we stop? When we find an element which is smaller than xk plus 1 or equal to xk plus 1, right? So let's say in this case, x2 happens to be smaller than xk plus 1. It means that all the, from x3 to xk, all the elements were larger than xk plus 1. So we have shifted them by one position to the right while maintaining their own ordering, right? So x3 up to xk, their ordering will remain the same. It's just that between x2 and x3, I have a gap. And there I'm going to finally place xk plus 1. Okay, so this is how the insertion sorting works. So when you are in this k plus 1 iteration, you will have to make comparisons in the worst case with all these k elements. So in the first iteration, when you just want to, first iteration, x1 is already sorted. And then you come to x2, you compare it with x1. Based on the comparison, you are going to sort x1 and x2. Then comes x3. Right? So again, you'll compare it with x2. Okay, if x3 is larger, then we know that x1, x2, x3 is the sorted array, and so on and so forth, right? So if I have x1, x2, x3 already sorted, and now I want to know the position of x4 with respect to this sorted array, I'll compare it with x3. Let's say x3 is larger, so shift it one position right. Then I compare it with x2. Let's say x2 is also larger, shift it one position to the right. Then I compare with x1. Let's say x1 is also larger. I'll shift it one position to the right. And then there is nothing to the left of x1. I'll place x4 here. Okay? So it's just about finding the right position of this next element in this sorted list. So in the worst case, you might have to shift the entire first k elements to the right. Right? So the kth iteration is going to take k steps. Okay. So in that way, we can again find the running time of this algorithm, which will be the first step. I'm going to take order one time, then two comparisons, and so on and so forth up to n minus 1 comparisons, which again will be this will be n into n minus 1 by 2, which is order n squared. So I hope this selection sort and insertion sort is clear to all. Now, in selection sort also, after every iteration, if you look at the first few elements of the array, they are sorted, right? So let's say after k iteration, we know that x1, x2 up to xk, these are sorted. Same happens in the insertion sort also. After every iteration, there are some, the prefix of the array is sorted, the k prefix. Now, if I ask you what is the basic difference between selection sort and insertion sort, with, let's say, in the context of the sorted sublist that you see, can someone explain that? So specifically, my question is, in case of selection sort as well, after k iterations, I have a subpart, a prefix which is sorted. So this is sorted. And then the remaining list is unsorted. Xk plus 1 up to xn. And after each iteration, we want that this sorted list grows by 1. So after once these are sorted, once I have that this part is sorted, then after the next iteration, I want that the first k plus 1 elements must be sorted. Then the same thing happens in the case of insertion sort as well. What is the difference between these k elements in the selection sort versus these k elements in the insertion sort? How do these elements differ? Is the question clear? You have the input list x1 to xn. You have these two algorithms. One is doing the selection sort. Another algorithm has is based on insertion sort. My question is, in the middle of the all the iterations, let's say after k iteration, selection sort will give you a list where the first k elements are sorted. Insertion sort will also give you a list where the first k elements are sorted. Are these elements the same or they are different? How do they, if they are different, how, in what way they differ? Is the question not clear? Yes, that is true. So in insertion, some kind of shifting, there is a shifting involved, and in selection that is not there. My question is, so first thing is that I give the same input to both these algorithms, right? The same set of elements, same set of n elements to both these algorithms. And after every iteration, I'm looking at the the list that I am obtaining, right? The what is the sorted part and then the unsorted part. Now, after k iterations, we know that both the sorting algorithms will have the first k elements sorted. That is correct, right? The first k elements will be sorted. Now, of course, they are not the same because the algorithm is working in the different, both these algorithms work in the different ways. So they are not same. Now, my question is, how do they compare with the elements in the, what ways do they really differ? In insertion, elements should be relatively sorted, not the absolute ones. This I didn't. They are sorted. whether in the relative sense or in the absolute sense, they are sorted, both are sorted. But how do these two sublists differ? Okay, forget about the insertion for now. What can we say about these first k elements? Where are they coming from in the selection sort? What is this x1? This is the smallest element in the entire array. X1 is the smallest element, right, in the selection sort. Here, X1 need not be the smallest array, smallest element in the entire array in the case of insertion sort. So X1 is the minimum element, X2 is the second minimum element. Right? So after k iterations, the sorted sublists that I obtain, these are essentially the first k smallest element in the input array. Right? So here, this is the first k smallest elements in the input. So the key here is that these are the smallest elements. Okay. What about in the insertion sort? Yeah, they may not be the least k elements. These are essentially the first k elements of the input array, right? So here, because we are not really seeing the entire array in every iteration. In case of insertion sort, initially we are just looking at the first element, then the first two elements, first three elements. So after k iteration is the first k elements of the input array itself which are sorted. So that's the key difference between selection and insertion sort. So over here, these are the first k elements in the input, which are sorted. So that is how the working of selection and insertion sort differs. Both have the worst case running time of order n square, but they differ in their approach, right? So here every iteration you are finding the minimum element. So after k iteration, your first k elements which are sorted, they refer to the first k smallest elements in the entire input. In case of insertion sort, when you have performed these k iteration, the first k elements itself get sorted. Whatever is your input array given to you, you just look at the first k elements, they will be sorted. Okay. Now, what do we mean by stable sorting? So sometimes if the elements are not all distinct, some elements have the same value, then, so let's say I have student names and their marks in a course, and let's say two students have obtained the same mark, right? So if I want to sort that list by the marks obtained by the students, then a stable sorting algorithm will not change the relative ordering of the students who have obtained the same marks. So stable sorting, let me give a simple example here. Say I have, say we have 4 students, say A, B, C, and D, and their marks are as follows: 67, 70, 79, and 67. Okay. So let's say these are the marks obtained by the students. Now I want to sort this list by the marks. Then I can have two sorted lists, right? So one is, I'll have A first, D, C, B, and C, right? And their respective marks are 67, 67, 70, and 79. And I can also have a sorting algorithm which will produce the following output. It can generate D as the first element in the list, then A, then B, and C. Right? So 67, 67, 70, and 79. Now, which of the two outputs are stable, first one or the second one?
First one is stable.
The first one is stable. And because in the input we had A and D, they both had same marks, 67, but A occurred before D. Right? So a sorting algorithm is stable if it maintains this ordering. Right? So in the sorted order, A must come before D. Then it is a stable sorting algorithm. This is also sorted, but since the ordering has been changed, it is swapped, this one is not a stable output. Okay. Now, is selection sort stable? Okay. What about others? Selection sort is stable or not? Actually, it is not. It's not stable. Okay, but giving the answer, it is not stable. Now, can you think of a smallest example and then run the selection sort on that example to see that it is actually not stable? Can you give a short example? Let's say just 3 elements, because 2 elements must be same, and then the third element is different. Apply selection sort to that input of 3 elements, and you will see that you should be able to see that it is, it's actually changing the ordering of the elements which were same. So think of an example where you have 2 elements whose values are same, third element different, and then the selection sort will give you a list which is not stable. Okay, let's say I have 3 elements, A, B, and C. I have a simple example here. Let's say I have 3 elements, A, B, and C. The values are as follows. So this is 5, 5, and 1. Okay. So essentially, I have 3 elements, 5, 5, and 1. And I want to sort this list using selection sort. How does it work? It will go and find the minimum element. The 1 is the minimum element. And you will swap these two, right? So what I will have is, after sorting, what we get is 1, 5, and 1. Sorry, 1, 5, and 5. Which means that C comes first, then it is B, and finally A. Because in the second iteration, again, you go and find the minimum element. The minimum element will be 5. So you just swap it with itself, right? So B stays at the same position. And then in the third iteration, again, you find the minimum element, which is, again, just one element, swap it with itself. So the final list that you get is C, B, and A, right? So the ordering of A and B has changed in the output. That is why it is not stable. Is this clear? Why is selection not stable?
Yes, ma'am.
And what about insertion sort? Is that stable? Just think of how it works, how insertion sort works. Do you think it is stable? See, just try applying insertion sort to this simple example itself. You should be able to answer for any input. How is insertion going to work here? You forget about the first 2 elements. Initially, this one element sorted. Then you look at the first 2 elements, right? So, I mean, you want to insert the second element at the correct position in this sorted list. But here 5, you compare with 5, both have the same value. So you don't shift anything, right? So no shifting is there. So 5, 5, right? Means A and B, they maintain their ordering. And then third element 1, you compare it with the previous element 5. So 5 moves right. I mean, the element B, whose value is 5, moves to the right. Again, you compare 1 with A, value is larger. So that will also move right. So what you will have is C, A, and B. So in here also, you are not changing the ordering of the elements which have the same value. So in any example, and this is just one example, if you take any input, no matter how the what the values are, how many elements have the same value, and if you when you apply this insertion sorting, you can always implement in a way that it stays stable, right? Because it's only going to shift the elements which are strictly larger than the current element to the right. Okay, so in that way, insertion sort is stable. That's another difference between selection and insertion sort. Okay, I'll take a break here, and then we will do we'll take a different problem, and it's an interesting problem, a geometry problem we are going to take, where the input will be a set of points, and we'll have a certain goal. Okay, in fact, let me define the problem, and then maybe during the break, you can think of an algorithm to solve the problem. After the break, we will then discuss the algorithm. Let's say the problem is you have points in the plane, that is your input, right? And in the plane, I mean that every point will have two coordinates, x coordinate and y coordinate. And so imagine these points in the plane. And, okay. So let's say that, let's say you have a plain paper, you have marked the axis, x and y axis, and you have those points, right? X and y axis, and you have the points. Now, what I want is, we want to compute something called as the convex hull of these points. So I'll quickly take a simple example. Let's say these are the points. Okay. And we want the convex hull of these points. Right? So convex hull. What I mean by this is, so imagine these points lying on a flat surface, okay, with some flat surface, and let's say you have some pins on these points. At every point you have a pin, and then you have a string that you want to wrap around these pins so that all the points are enclosed within the wrapped string. And the goal is that when you wrap around that string to enclose all the points, that string must have the smallest perimeter, smallest area, smallest size, right? So what I'm essentially looking for is this kind of shape. Change the color. Okay, I had points in the plane, and now you imagine that at every point I have a pin, every point, and I'm going to stretch a string around these pins so that I'm able to cover all the points. All the points must lie inside or on the boundary of the string, and the perimeter of this string must be as small as possible. Okay, so for that, it's going to be of a specific shape. The shape is a convex shape. Okay. And this polygon that we get, right? A polygon means it's a closed figure which is bounded by straight lines. This polygon that we get, which has a convex shape, is known as the convex hull for the set of points. Is the problem somewhat clear? If you're seeing this for the first time, are there any doubts? What is the input here?
X and Y coordinates of n points.
Yeah, so every point has an x and y coordinate, every point. So let's say I have n points, that is the input, right? For every point I have x and y coordinates. And as the output, what I want is, I want these points which lie on the boundary in this order. Right? I must be able to report these points either in clockwise order or anti-clockwise order. Let's say I want to report them in clockwise ordering. From any point you can start, and you should be able to report these points. So these points form the vertices of the convex hull. These are the edges of the convex hull. So anyways, we are not really, the convex hull shape itself is formed by these vertices and edges, but our algorithm must be able to report these points in clockwise order or anti-clockwise order. Okay? So once I know that, okay, here are the vertices, I can also find the edges. So the output must be these vertices which lie on the boundary of the convex hull. And why it is called convex? So you must have, or maybe, I don't know, so you must have studied these objects can be either convex or non-convex. By convex, what we mean is, if you have any closed shape or even unbounded, it can be unbounded also, it can be bounded as well. So suppose you have, for simplicity, let's assume it's bounded and closed. You're given a shape in 2D. It's some shape in 2D. And if I ask you whether it is convex or not, the definition goes like this. So let's say I have something like this. So is it convex? So the definition is, if you take any 2 points within that shape, within that region, and you connect it by a straight line, those 2 points by a straight line, then the entire straight line, that line segment must lie within the region. So here, for instance, this is not convex, because if I take, let's say, this point and this point, and I connect them by, should have drawn the figure. The figure is like this. And now I take, let's say, these 2 points and connect them by a segment. Then there is a part of the segment which is lying outside the figure. Okay, so this is not a convex shape. The black shape that I have drawn is not a convex shape. Whereas something like a circle or ellipse, right? Those are convex shapes. This is a convex shape, because here, no matter where you take the 2 points, I take a point and you connect them by a line segment, the line segment is always going to lie within the figure. You can never have 2 points such that the line segment joining them lies outside the figure. Some part of that line segment is outside the figure. So such a shape is called as a convex shape. So this is non-convex, this is convex. Now we are not interested in these kind of shapes. We are rather interested in polygons. So we can have polygon, meaning where the shape is bounded by straight line segments. Right? So something like this. This isn't a convex polygon, right? For the same reason, because I can take points and connect them by a segment, there is a part of the segment which is lying outside the polygon. So this is non-convex. Whereas the example here that I have drawn, forget about the points for now. If I take this polygon, this is a convex polygon. So no matter where you take 2 points, if you connect them by a line segment, the line segment will lie entirely within that polygon. Okay, so is this clear? What do we mean by a convex polygon? Is the definition of convex polygon clear? Yes or no?
This is convex.
Yeah, this figure that I just drew is convex.
Yeah.
So is the definition clear? Convex and non-convex polygons.
Yes. Yes.
Yeah. So in the convex hull problem, we are essentially looking for the smallest convex polygon which encloses all the points. Okay, so that is the problem that we want to solve. You can think of some algorithm. You're given a set of points in the plane. You want to find the smallest polygon which encloses all the points, all the given set of points. Okay, so that polygon is a convex polygon, which is also known as the convex hull. The question is find the convex hull. Essentially, find the vertices of the polygon in a particular order. So we'll discuss the algorithm. We'll take a break now. 7-8 minutes, and then at 4:12 we will resume. Okay. Please stay connected. Is the problem definition clear? The convex hull of a set of points? This time I'm not really enjoying teaching, taking these sessions. People are very slow. Even in the yes, no kind of things, you are taking a long time to answer. Last time it was much, much better. The sessions used to be very, very interactive. This algorithm, this problem itself, I could cover in the week one TA session itself. Today, my plan was to cover this, another interesting algorithm from geometry, but people are not responding. It's simply slowing down my pace and slowing down. It's not even helpful for you, right? You will not be able to learn much this way. Is the definition clear? Problem definition.
Definition is clear, but you are saying the minimum number of points to be fit.
Not minimum number of points. I want to pick a subset of the points. Convex hull of P is a subset of the points, such that the polygon that I obtain when I connect those points, I'll get a polygon, right? A convex polygon. This polygon must be as small as possible, in the sense that the perimeter wise, area wise, that must be smallest. So for instance, there are multiple ways to cover this with a polygon. I can have a polygon which is something like this. Okay, this is also a polygon, right? Assume all these are straight lines. But is this the smallest polygon that covers all the points? Again, the smallest, let's think of this in terms of perimeter. Does this polygon has the smallest perimeter? And let me give you the actual smallest polygon as well, so that you are able to see the difference between the two. So here is one polygon which covers all the points. And then here is another polygon which covers all the points. Which of the two has the smaller perimeter? The blue one or the orange one? I mean, some edges were common, so the blue and orange is giving us a green edge. But is the orange one has the smaller perimeter or the blue one has the smaller perimeter? The perimeter is simply adding the lengths of the edges, right? Yeah.
Orange ones looks
The
smaller.
orange one, right? Orange one has, even if you take just compare this edge, I mean, I wanted to connect this point with this point. So this edge has definitely smaller length than something like this. Yet by triangle inequality, if you have a triangle, then any side will have a smaller length in comparison to the sum of the other two sides. So the orange one is the smaller. This is the polygon I'm looking for. The smallest one which covers all the points. I could have taken even a larger polygon, right? I could have taken something like this as well. This is, oops, this is no more a polygon. And this is also a polygon. Huh. Yes.
The blue polygon is not convex.
This is not convex. Blue is not convex. This is convex, right? But this is not the optimal polygon I am looking for. This is larger than what is required. The optimal one is the orange polygon, and that has to be convex. So you can think about it, why the smallest polygon that is required to cover, that will cover all the points has to be convex. Just try to make it non-convex, right? Take one edge and make it non-convex, either way. And you should be definitely immediately able to see that, then it is not a convex polygon, plus the perimeter is going to increase. Okay, even if you keep it convex and make it larger, then again the perimeter is going to increase. Okay. So I hope the definitions are now clear. Is there still any doubt? Yeah, you can also think of, let's say you want to you want to gift something to your friend, and it has some planar shape. Okay, it has some planar shape like this, and now you want to wrap it with a string. Do you want to use, the strings, you want to optimize the amount of string that you use. So you should not be using more than the required length of the string. It's again the shape that the string will assume when you wrap all these points with the string. That shape is actually the convex. That shape has to be the convex shape. Okay. That is what we mean by the convex hull. Now, in terms of the computational problem here, uh, what we really want as an output is some subset of points which will form the vertices of that convex polygon. And we do not want them in any arbitrary order. Like, for instance, this is the polygon I'm looking for. So I want to report these vertices, but in a specific order. It's not that I'm going to report this one first, then this one, then third, fourth, fifth. No, that will not make sense to me, because if I were to report it in this order, let's say like this, then the polygon shape would be something like 1 to 2, then 2 to 3, 3 to 4, 4 to 5, 5 back to 1, which is not a polygon which is enclosing all the points. So that is the reason we want to report these points in clockwise or anti-clockwise order, right? So in clockwise order, I'll report these points, and then the polygon actually has the shape I'm looking for. So that is the relevance of this ordering, why we want a clockwise or anti-clockwise ordering. Okay. Now, can you think of a simple algorithm to find the convex hull, find these points? So, for instance, if I give you these set of points and now you have the understanding of what a convex hull is, can you say which points will be there in the convex hull? Those points must be there in the convex hull. So every point has x coordinate and y coordinate. Which points you think must be the part of the convex hull? Let me give you some hint. Forget about the y coordinates. Look at the x coordinates of the points. Now, which points do you think must be there in the convex hull? Okay, what can we say about the point which has the minimum x coordinate? Will that be a vertex of the convex hull or not?
Yes, it should be.
It should be, right? So here, for example, in this set, this point has the minimum x coordinate. I'm going to call that as the leftmost point. And that point must be part of the convex hull. I cannot miss this point. Right? Similarly, point with the maximum x coordinate also has to be in the convex hull. Point with the maximum y coordinate has to be in the convex hull. Point with the minimum y coordinate. So all these 4 points, the extreme points, points with minimum or maximum x coordinate or y coordinate, they have to be there in the convex hull. Right? So you can start with one of these points, right? So let's say I start with the leftmost point, and now I want to find the next point in this convex hull, right? So in the clockwise order, which is the next point? This is the next point. So question is, how do I find this next point? Once I have found this point, that means this part I have identified, I want to find the next point in the convex hull, which is going to be this point, right? So after finding these 3 points, I want to find the 4th point in the convex hull, then the 5th point in the convex hull, and finally, when I go on and find the 6th point, it happens to be the point where I started with, and there I can, we can stop. Right? So it's an iterative process. In every iteration, so I start with the leftmost point. You can start with the topmost or the bottommost or the rightmost point. So let's say we start with the leftmost point, and then at every iteration, I'm going to find the next point in the clockwise ordering. Okay, so here is the key observation. Assume that you are standing at this point. Okay, so let's say you are standing and facing all the points. So since you are standing here and facing all the points, you must be able to see all the points, right? Because this is the leftmost point. You should be able to see all the points. And now, of all these points, you want to find the point which is rightmost, sorry, which is leftmost. Now, which of these points is the leftmost point? Let me just number these points. Let's say they are stored in an array. Let's say this is 1, 2, 3. So these points are stored in an array in this ordering. This is the point number 1, then point 2, point 3, point 4, point 5, 6, 7, and 8. Okay, so that was the first point, second, third. So first of all, you scanned the entire array and you found, you were looking for the point which has the minimum x coordinate. So that is point number 5. You select that point. Now I want to find the next leftmost point. So if I'm standing here and I'm looking at all the points, which is the next leftmost point? So by leftmost, I would mean that if you look at that point, right? So, okay, if suppose I look at the point number 7, I'm looking here, then all the points, all the other points must be to the right of it. So that point will be the leftmost point. So with respect to point number 5, point 7 is the leftmost point. Can you see that?
Yes.
Yeah. So if you are standing at 7, and so let's say you have an oracle, you have another algorithm which will always give you the next leftmost point. Then the algorithm is very simple, right? You will say, okay, I'm standing at point 5, give me the next leftmost point. It gives you 7. So you go on and then stand at 7. And then of the remaining points, again, you ask that second algorithm, give me the next leftmost point. So if you are standing at 7 and looking at all the points, forget about 5 for now. If you're looking at all the points, then which is the next leftmost point?
Then it is 6.
It is 6, right? And you continue that way. So standing at 6, looking at these points, sorry, the remaining points, find the next leftmost point. It's going to be 4. Then at 4, find the next leftmost point, 2. When you are standing at 2, looking at the remaining set of points, you'll see that the next leftmost point is going to be 5. But that was the point you started with, and there the algorithm will terminate. That is how you are going to compute the convex hull. So essentially, it is about finding these vertices with respect to the point. Some points you have already selected, and in every iteration, you want to find the next leftmost point, as if you were standing at the previous point and looking at all the remaining points. Okay, so I'll quickly write the algorithm here. It's whatever I had explained to you, that I'm just going to write in terms of pseudocode. So let's say the leftmost point is that point number 5. I store in some variable L. Now the key question here is, how do we find that leftmost point? Oh, sorry, the next leftmost point. Right, so it's like the selection sorting algorithm, right? In the selection sort, first of all, you find the minimum element. So you have to scan the entire array and then find the minimum element. In each iteration, you actually find the minimum element in the remaining set of array. The same thing we are doing here. Here, it's not the minimum, it's the leftmost element, leftmost point. Okay, let me write the algorithm, and then we will see how to actually find the leftmost point. So that is the leftmost point. I need to use 2 more variables here. So the points that I am going to select will be in P, the current point that I'm selecting, it's in P. So whatever is the leftmost point, I select it. Oops. Okay, and then we are going to repeatedly compute the next leftmost point. It's a repetitive, it's going to be a loop. So we will in every iteration, we are going to find the next leftmost point. Let's say I have an oracle that is returning me the next leftmost point. I'm going to store it in Q. And here I call another algorithm, which will return me the next leftmost point. Okay, and this also I select. So I store it in Q. And we will keep doing this until we reach back to the starting point. So while P is not equal to L. So as long as I'm getting different points, I'll keep adding them. And once I come to a point where the next leftmost point happens to be L, then we exit from the loop. Right? So that's the simple algorithm to compute the convex hull. The only piece that remains to be implemented is this. How do we find the next leftmost point? So is the overall algorithm clear?
Yes, ma'am.
Yes. And if I tell you that, okay, let's say that this piece, finding the next leftmost point, it takes order n time, then what is the running time of this overall algorithm? Suppose I can implement this step, finding because it's like I have an array and I want to find the smallest point. Here I want to find the leftmost point. So let's say I can do it in order n time. I'll tell you how to do it. Let's say we can do this in order n time. Then what is the overall running time of the algorithm? Finding the leftmost point, this takes order n time because you have to scan the entire array. Forget about the y coordinate, just look for the point which has the minimum x coordinate. So that is essentially finding the point with the minimum x coordinate. This will take order n time. Right? My list is not sorted with respect to x coordinates, so I'll do a linear search, find the minimum element. This will take order n time. Then this next is the simply assignment statement, which will take constant time. Here also this step takes order n time. This will take order 1 time assignment. So the key question is how many times do we need to perform the number of iterations which are required. So once I know how many times we need this do while thing, we should be able to compute the overall running time of the algorithm. So let's say that the convex hull of P has k vertices. So because what is happening is in each iteration, I'm actually obtaining a vertex of the convex hull, right, in each iteration. So we started with 5. Then in this first iteration of the loop, I'm going to find 7. Next iteration, I'm going to find 6, then 4, then 2. So overall, how many iterations are required? If I have k vertices in the convex hull, how many iterations are required?
Four.
Yeah, so it is order k, right? One less because in every iteration, 5 I had already found. The remaining k minus 1 iteration I'll need to perform. So the number of iterations is that is k minus 1. So the overall running time will be how much it is? In each iteration, I'm going to take order n time, order n plus order 1, it is order n. And I'm going to repeat it roughly k many times. So the overall running time of the algorithm will be what is the running time?
It should be n squared.
Okay, so you are trying to think of the running time in terms of n, just n. So you are absolutely right. This k is at most n. K is at most n, less than or equal to n. So the running time in the worst case, it's going to be order n square in the worst case. But you know, I had told you that when we want to analyze the running time of an algorithm, we always we use the input parameter, right? And we define the running time in terms of the input parameters. Here, in geometric algorithms, mostly in geometric algorithm, there is something called as output sensitive algorithm. This is what we call as output sensitive algorithms. What it means is that the running time will depend on the input size as well as the output size. Because here I can, what I had was, okay, we have k iterations, and in each iteration I'm taking order n time. So running time, I can quickly say it is order n times k. It's order n times k. And then you were right to say that it is order n square in the worst case, because k is at most n. But this is also a way to uh, express the running time of an algorithm. Sometimes, I mean, we will not see much of these such algorithms in this course, but this is one example where the running time is not just a function of the input parameter, but also a function of the output parameter. So such algorithms where the running time depends on both the input and the output size, they are known as output sensitive algorithm. This is an example of an output sensitive algorithm. Okay, usually our running times are functions of just the input sizes, but some algorithms where you will be able to see that, okay, maybe we can give a tighter bound on the running time, then you should, think whether there is another parameter in terms of which I can define my running time. It's, I mean, whether it's the input also which defines the running time of an algorithm. So in that case, you will have a function that depends on both the input and the output parameter. Okay, this is also correct.
But ma'am,
Order n squares.
that is okay. But ma'am,
Yeah,
this value of k is known only after the entire problem has been solved. No?
that is correct. That is correct. So let's
So
say that you are right. So n is known to us because that is the input. K is not known to us because that is going to be the output. What we are saying here is, let's say k is the size of the output. We do not know what the size of the output. Let's say k is the size of the output. Then the running time of my algorithm is order n times k, assuming k is the output size. And k is not known to us. In the worst case, k can be at most n, and therefore the running time is order n square in the worst case. So why we, if indeed my algorithm depends on both the input and the output size, then it is preferable to give a tighter bound. Why it is so? Because you see, the output size can be much smaller than n also. Right? For instance, if I have a huge set of points and the entire set of points can be enclosed by this smallest polygon, which is actually a triangle, then k is only 3. And in that case, this algorithm is going to work much faster than an algorithm which does not depend on k. So let's say I have two algorithms. One algorithm has a running time is a function of has a running time, let's say nk, and there is another algorithm whose running time is order n squared. And now you give the same input to both the algorithm. The first algorithm, and both will compute the same convex hull, because for a set of points the convex hull is unique. Let's say the convex hull has a constant number of vertices. Okay, so smallest could be 3, 4, 5, like that, and n is huge. Then the first algorithm whose running time is order nk is actually order n because k is constant. Whereas the second one it has a worse running time than this one. It's order n squared. Okay, so that is why we are also interested in output sensitive algorithms. And does that answer the question?
yes, ma'am.
Yeah. Okay. Okay, so the only thing that remains is how do we find this next leftmost point, right? So all these points are stored in an array, and we have found the leftmost point. This will be at some index in the array. It's at index 5 in this example. And with respect to this point, I want to find the next leftmost point, which is 7. So how are we going to do that? So for that, we need to understand a basic problem in geometry. Let's say I have 3 points, P, Q, and R. Um, In fact, let's say I have 2 points, P and Q. So I can connect them with a line which starts at P and then goes through Q. And there is third point R. This point R in a third, so think of like this. You have 2 points, then 2 points will be connected by a line, fine. Then there is third point. That third point could lie either in this line, which will mean that, so let's say the third point is R. So if the point lies on this line, point R, in that case, we will say that P, Q, and R are collinear. They are lying on the same line. Or it could lie somewhere in the left, I mean, in one of the two halves, right? For instance, if R lies here, then we will say that R is to the left of PQ. Right? So when I say PQ, I mean the segment in this direction, P to Q. So if my point R lies somewhere here, then, or in fact anywhere in this half, then we will say R is to the left of PQ. Whereas if it lies in this half, the point R lies in this half, then R is to the right of PQ. Okay, so here R is to the left of PQ. I'm looking at the directed line segment from P to Q, and this side is right of PQ. Now, given 3 points, P, Q, and R, it's in a constant time we can determine whether R lies to the left of PQ or R lies to the right of PQ. Right? So you can think about this offline. It's a simple problem. Given 3 points, finding whether the third point lies to the left or to the right of the first 2 points. This can be done in constant time. I'm going to call that primitive as a so in geometry, that is a standard, not a standard, but most commonly it is referred to as a counterclockwise test, CCW test. CCW, counterclockwise, and it will take as an input 3 points, P, Q, and R. And what it will tell us, it will return a number, negative, positive, or 0. It is equal to 0 if P, Q, and R are collinear. Same line, or it will be less than 0 or greater than 0. Okay. So less than 0, if it is to the right of PQ, depends really on how you are implementing it. Let's say we implement it in a way that less than 0 means R is to the right of PQ, and positive means R is to the left of PQ. Yes. So if you think about this, you can do it by computing the slopes. Okay, so essentially you can compute the slope of line PQ, QR, or PR, and then comparing these slopes, you should be able to implement this function. And since it only involves computing the slopes and then comparing the slopes, this entire function can be implemented in constant time. Okay, CCW, you can implement this in constant time. This you can think about offline. So for now, you assume that you have this function at hand, CCW. It will take 3 points and it's going to return me the orientation of third point with respect to the line segment going from P to Q. So it's a directed line segment going from P to Q. Is the purpose of CCW clear?
Yes, ma'am. This is required for verifying whether all the points are to the left or to the
Yeah,
right.
we will use
Starting from
this in, yeah, we'll use this in this problem, but as a standalone function is the is the functionality clear, like what it is going to do and what does the value mean?
yes.
So now let's see how do we use this to find the next leftmost point, right? So coming back to this problem, we have all the points in an array. So let's say that I have this array of points. Okay, and these points are stored in the array. At some index, I'll have my point P. Just changing the indices here so that it looks. So suppose the point P was at index 3. Point P is here. Now I want to find in the, think of this first iteration. I'm going to find the next leftmost point. Okay. And that I'll store in the variable Q. So when I'm looking for the next leftmost point, I do not know, it can be any of these points or the points before P or the points after P in the array. It can be anywhere. So I start at this point, the point which is after P, right? So think of this as a circular array. So if P was here, then I would have taken Q to be the next point, which is the first point in the array. So think of this array as really a circular array. So you have this P, which is the leftmost point. Initially you think, okay, maybe this is the next leftmost point, but then you have to actually scan the entire array to find this right Q, right? So uh, again, the analogy is with the array, with the problem of finding the smallest element. So what do? Uh, you want to store the smallest element in some variable Q. So initially you take Q to be equal to the first element of the array, right? And then you go on and scan the entire array. Wherever you find an element which is smaller than the current Q, you update it. And that is how you finally get to find the smallest element in the array. The same thing we are going to go do here. The next leftmost element can be any point other than P, right? So I'm just going to initialize Q to the next point next to P, right? So here is Q. And then whenever I find a point in the remaining array, which is to the left of PQ, I'm going to update Q. Okay, that's the main idea. So I need to iterate over the remaining array. So for that, let me take a different variable, say R. So I take a variable R. Now R is, P is at index 3 in this problem. P is at index 3. Q is at index 4. I take R to be at index 5. So whatever is the next index, right? So if P was here, Q were here, then I would have taken R to be here. So R is the next index. And now you apply CCW on this P, Q, and R. So CCW, let's say, forget about 0. Assume that no 3 points in your input are collinear. Okay, so it will either return you a less than a negative value or a positive value. So you apply CCW to PQR. In which of the two cases are you going to update Q? Take this example itself. This is P, this point is P. Okay. Currently, this is Q because that is the point sitting at the next index. So P is at index 3. I take the point at index 4 to be equal to Q. And point at index 5 is equal to R. This is R. So in this scenario, with P here, Q here, and R here, are you going to update Q to equal to R?
Yes, ma'am.
Why would we update? See,
I mean,
we want the point which is leftmost. Okay. And here, if you see, R is to the right of PQ, isn't it?
oh, no, no. For leftmost point, we need not update it.
Yes. So since we are looking for the leftmost point and R is to the right of PQ, so R is of no use to me. I mean, this point is of no use to me. I'm not going to update my Q, right? So what I will do, I'll move to the next point in this list. Okay? So this R is going to iterate over the entire array other than the P and Q. It's going, we are going to scan the entire array. So the next R position is 6. This is R. Now are we going to update Q to be equal to R? What is the orientation of R with respect to PQ?
Now R is to the left.
R is to the left. So, initially I had this as the current leftmost point, but then we find a point which is to the left of this point. So this cannot be the leftmost point. So I'll update Q to be equal to R. Right? So this is my current leftmost point. Then I'll move to point number 7. Right? So R is updated to 7. And again, we see that with respect to current P and Q, this R is to the further left. So we will again update Q. So we'll update this Q and make it equal to R. In the next iteration, R will be equal to 8, the index number 8. But here we see that R lies to the right of PQ and we do not update Q. So this is how we will proceed. So here I had just 8 points. Here the uh, this algorithm, this finding the next leftmost point will stop and it will give me the current Q. Okay, so that is the next leftmost point. Is the algorithm clear now?
Yes, ma'am.
Yes, right. So once you have these 2 points, forget about these 2 points and then again find the next leftmost point. Okay, so you will need a variable R to iterate over the remaining set of remaining set of elements in the array. And whenever you see that R is to the left of PQ, you will update Q to be equal to R. Okay. So since in every iteration, I'm going to scan the remaining array, uh, the remaining elements in the array, the number of iterations, that we need in the worst case will be order n. So it will keep on reducing n minus 1, n minus 2, and likewise up to 1. But overall, the running time will be order n times k. Okay.
Okay.
So that is the convex hull we will obtain. Okay. Assume this 1 is not really there. Yeah, so that completes the discussion on convex hull of a set of points. So any doubts in this algorithm, problem statement or algorithm? Minimum value of k for a set. Yeah, so if we have by k, I think we mean this output size of the convex hull. Yeah, so the minimum is going to be equal to 2, assuming that assuming that the points are not collinear. If all the points were collinear, in that case, my convex hull size will be just equal to 2, the first point and the last point, if all the points are collinear. If not, then the minimum value of k can be equal to 3. Okay, and that is why, because this, k can be equal to 3. Let's assume that not all the points are collinear. That's a degenerate kind of an example. So assuming that k's value can be as low as 3, that is why such an algorithm where the running time depends on both n and k is preferred. In that case, when k is constant, 3, 4, 5, or even log n, this beats any algorithm which has running time order n square. Yeah, so any other question? Okay, so thank you all for attending. I'll stop the recording here. We'll have the next session on 8th of August, Saturday, at the same time.